Lecture 37, Nanomaterials, Synthesis and Structure. At the end of Wednesday's class, we began to talk about how to image and manipulate nanostructures. We learned that visible light cannot be used to resolve nanostructures because the smallest feature that we can see with visible light is around the order of 400 nanometers. We learned that we could use scanning electron microscopy to visualize nanomaterials, since by changing the voltage, we can tune the wavelength of an electron beam to see smaller and smaller structures. We can also take a look at probe microscopy. In scanning probe microscopy, we can produce 3D images that can be used to manipulate individual atoms and nanomaterials. There are two types of scanning probe microscopy that's useful in imaging and manipulating nanomaterials. The first is scanning tunneling microscopy. Tunneling is a quantum mechanical phenomenon. To explain tunneling, think about pushing a ball from one side to another, where there's a hill in the way. Classical physics dictates that you would have to push the ball over the hill to get to the other side. This is also true in chemical reactions. Remember that when we talked about energy profiles, that reactant molecules must reach a transition state structure dictated by the activation energy in order to form products. This creates an energetic barrier or hill that the reactants must surmount to become products. In quantum mechanics, however, it is possible to go through the hill to get to the other side. This takes potentially less energy and does happen in chemical reactions quite often, especially when chemical reactions require small particles that obey the laws of quantum mechanics, such as electron transfer and proton transfer. In scanning tunneling microscopy, a metallic tip is brought close to a conductive surface, and a voltage is applied between the surface and the tip. Electrons can then tunnel through the space between the two surfaces to create a current. The amount of current depends on how far away the tip is from the surface. This allows us to probe different surface features and also move around atoms. This picture is an STM image of graphene from the National Physics Laboratory. You can see the hexagonal honeycomb structure of the single sheet of graphene, a feature that is resolved using scanning tunneling microscopy. Note that the surface does have to be conductive. Graphite or graphene is a conductive surface. This technique can also be used to visualize gold, silver, and other metallic nanoparticles, nanosurfaces, and nanowires. The second type of microscopy can be used for any type of material. This type of microscopy is called atomic force microscopy. In AFM, we use a tip made of various materials brought very closely to a surface or a material of interest. We use the forces between the tip and the imaging material to generate an image. These forces can be intermolecular forces such as hydrogen bonding, dispersion forces, solvent-solvent interactions, or charged interactions. The tip of your of your AFM is attached to a cantilever whose movement is monitored by a laser beam, which sends information back to a detector. There are two ways you can use an AFM. You can scan the AFM from side to side, noting differences in the surface texture of your material, or you can use a tapping phase where the cantilever is moved up and down and can be used to manipulate different nanomaterials. AFM has provided many advantages in imaging. The image on the left is an image of a DNA strand. Superimposed on the AFM image is a Watson and Crick diagram of the double helix structure of DNA, which the AFM image captures. The images on the right are truly amazing. They show a picture of pentacene, which is a molecule composed basically of 5 benzene rings fused together. The hexagonal pattern of the molecule is clearly visible in this image. Therefore, AFM has allowed us to be able to image single molecules as well as nanomaterials. These two types of microscopy show that many strides have been made to image smaller and smaller materials, driven by the pursuit of manipulating and imaging nanomaterials themselves. We now move on to how do we make nanomaterials. There are many different techniques used to make nanomaterials, but they fall into two major categories that each have their advantages and disadvantages. The first type that we'll talk about is top-down approaches. In a top-down approach to making nanomaterials, we make nanomaterials out of bulk materials. That is, we take a microscopic item, like a bar of gold or a silicon wafer, and pare it down to the nanoscale. A couple of top-down techniques include lithography, where etching is used to make nano-sized features out of macroscopic materials. A good example of this is making transistors on a silicon wafer. We can also process organic semiconductors using inkjet printing, where the features of the organic structures that make up the transistor are basically stamped onto the silicon wafer. Some of the disadvantages of using a bottom-up or top-down approach is that it is easy to introduce structural defects and impurities in these nanomaterials. For example, in lithography, a piece of dust can significantly affect the performance of a transistor. Therefore, when doing these methods are typically done in cleanroom situations, which can be very costly. The other approach is to use a bottom-up approach. In contrast to the top-down approach, bottom-up methods are used to fabricate nanomaterials atom by atom or molecule by molecule. That is, we start with individual atoms and molecules and build our materials using chemical reactions. Bottom-up approaches have the advantage of being dictated by free energy changes, which allow you to make materials with very few defects, because to minimize the free energy of the system would cause many of those defects to be excluded from the structure of the nanomaterial. A good example of a bottom-up approach is to make a self-assembled monolayer. The picture shown is how to make a self-assembled monolayer using a gold surface. Oligomers that have a carbon chain and a sulfur hydrogen bond at the end can attach themselves to the gold surface, creating a single layer of oligomer molecules. The making of this layer is dictated by minimizing the free energy of the surface, thus creating a defect-free structure. There are a variety of nanomaterials used for many different applications. We can classify these nanomaterials based on the number of dimensions that are not on the nanoscale. The simplest type are truly completely nano-sized structures, the zero-dimensional nanostructure. These are nanoparticles, where all dimensions of your nanoparticle are between 1 and 100 nanometers. An example of a zero-dimensional nanoparticle is the quantum dot. Quantum dots are nanoparticles that are between 1 and 10 nanometers. On this size scale, energy levels for the nanoparticle become discrete, meaning that the electrons go back to almost having certain energies instead of a multitude of energies for a larger nanoparticle or a bulk material. The small size of the nanoparticle leads to what we call quantum confinement. Since the electrons go back to having discrete energy levels in a quantum dot, this greatly affects how the particle interacts with light. This interaction is dictated by a process called fluorescence, when a system absorbs high energy light and then gives off a shorter wavelength of light or a lower energy of light once the absorption has happened. For a quantum dot, this fluorescence depends on the size of the quantum dot. Below are a picture of quantum dot solutions ranging from 2.3 nanometers to 5.5 nanometers. As you notice, the fluorescence color shifts from a light blue to a dark red. This observation can be explained by a simple model called the particle in a box, which greatly explains how quantum confinement works. For a small quantum dot, the energy levels due to quantum confinement tend to have a higher spacing, larger energy spacing. This means that when the particle absorbs ultraviolet light from the black light and then fluoresces the light as the electron falls from a higher energy level to a lower energy level, that photon of light will tend to have a shorter wavelength or higher energy. This higher energy photon will be much more blue shifted, since blue light has a higher energy than perhaps red light. For larger quantum dots, the energy levels are spaced more closely together. This means that when the quantum dot undergoes fluorescence, it will emit light with a lower energy or longer wavelength. This means that the photon of light will be redshifted. Therefore, the fluorescence of the quantum dot depends on the size of the nanoparticle, which affects the gap in energy and the energy of the photon that's emitted. Quantum dots have many applications. However, they are limited to experimental studies only in some cases. Quantum dot fluorescence and the size the color of your quantum dots depend on size can be applied to making LEDs that have different colors. In the LED, a layer of quantum dots are added so that when the electron and hole combine to give off light, the light will have a certain color. One research application is to use quantum dots to detect tumors in patients. The study has been confined to mice only, but the idea is to feed the mouse or human patient a sample of quantum dots that aggregate in cancerous tumors. These tumors can then be detected by simply shining a black light on the patient. This application is very limited because at the time, many quantum dots are made from poisonous materials such as cadmium, selenium, and sulfur. The next type of nanomaterials are nanowires and nanorods, the one-dimensional nanomaterial. This means that one dimension, the length of the nanorod or nanowire, is not on a nanoscale. However, the diameter of the nanotube is. A very interesting example of a one-dimensional nanomaterial is a carbon nanotube. You could think of a carbon nanotube as either a single or double sheets or multiple sheets of graphene, single sheets of graphite, rolled up into a tube. How you roll that graphene up to make the carbon nanotube will dictate its properties. The properties depend on the diameter, the twist, and the number of walls in the nanomaterial. Diameter dictates the shape of the nanotube. You may think that most carbon nanotubes are cylindrical. However, large diameter carbon nanotubes can collapse a bit under their weight and take a more flattened shape. Twist is related to how you roll up your graphene sheet. There are 3 types of twist for a carbon nanotube: armchair, zigzag, and chiral. Twist affects the electrical conductivity of the carbon nanotube, since it affects how the p orbitals from the sp2 hybridized carbons will line up to allow electrons to move throughout the tube. For example, armchair carbon nanotubes conduct electricity as well as metals, because this structure provides the best alignment of the p orbitals on a nanotube to promote the best electrical conductance. While zigzag and chiral carbon nanotubes tend to be good semiconductors, which have different applications. The number of walls can also affect the properties of the carbon nanotubes. A multi-walled carbon nanotube, because of its layers of carbon nanotubes, can potentially be a stronger material. In addition, multi-walled carbon nanotubes can be functionalized on the outside wall while keeping the electrical properties on the inside walls. This allows for carbon nanotubes to be used in multiple types of applications. For example, if the carbon nanotube must be dissolved in a water-based solvent versus an organic solvent, functionalizing the carbon nanotube with polar groups would be ideal. However, this would not affect how the carbon nanotube conducts electricity, which would be dictated by the inner walls. Here's some current applications for carbon nanotubes. Carbon nanotubes, besides being electrical conductors, are very much known for their strength. For example, if you would like to make a transistor that is flexible, it will not lose its integrity and usefulness if it's bent, carbon nanotubes are a good way to have these properties. Since carbon nanotubes are very strong, they will still conduct electricity even when the transistor is bent. Another interesting application of carbon nanotubes is their usage in sporting goods, taking advantage of their strength. Carbon nanotubes are typically used in tennis rackets, golf clubs, and other sporting goods. The third and last type of nanomaterials are two-dimensional nanomaterials. These are materials that are thin films or surfaces, where the height of the surface is on a nanoscale. However, the area of the material can be as large as you need. A good example of two-dimensional nanomaterials are piezoelectric nanomaterials made of molecular materials. You may have heard of the piezoelectric effect. This is a deformation of a material in response to an electric field. It could also mean that you take if you apply an electric field to a material, it causes a deformation. This is utilized in quartz watches, where an electrical pulse is applied to a quartz crystal, which then vibrates at a certain frequency and can be used to keep time. We can use molecules using the method of making a self-assembled monolayers as discussed before to make molecular springs or molecular piezoelectric materials. This can be done by pretty much stamping these molecules onto a gold surface, which in turn bond to the gold surface, creating your monolayer. Piezoelectric materials are useful as actuators and switches. For example, if you've ever received a birthday card that plays music or says a message, it probably utilizes the piezoelectric material. Opening the card deforms the material inside of the card, which then sends an electric signal, which then provides electricity to play the message or song or video. Nanotechnology has many applications, but there are some overarching drawbacks. Nanomaterials have the propensity to be made at a very low cost. For example, stamping, inkjet printing organic semiconductors onto surfaces to make transistors and solar cells can be very low cost. However, many of the methods that are used are pretty expensive. The price of making nanomaterials can come down if we focus on more bottom-up approaches using chemical reactions to make materials versus top-down approaches, which tend to be more expensive due to using clean room conditions. Some nanomaterials are actually very sensitive to defects and structural integrity. That is because defects can deeply affect. This is because defects, scratches, and other issues can deeply affect the performance of structures on the nanoscale. Nanomaterials, because they react very discreetly with light and other types of radiation, can incorporate defects such as dust into their structures during their manufacture. This is why making many nanoparticles have to be done in clean room conditions. For example, When making silicon transistors, we usually use lithographic methods which need to be done in the clean room. This also affects the cost of, of making nanomaterials, since cleanroom conditions can become very expensive. Again, switching to more bottom-up approaches where minimizing the free energy of your system dictates the formation of your nanomaterials will be more useful, since this method is usually prohibited a lot less sensitive to the introduction of defects. Since the minimization of free energy is oftentimes excludes defects from the structure. There are also some environmental or health risks. The problem with nanomaterials is we don't know a lot of those risks because nanotechnology is a relatively new field. Therefore, many nanomaterials can't be removed from our environment or recycled using traditional means. We also know that due to their size, nanoparticles can be unintentionally ingested, inhaled, or absorbed into the body. And oftentimes, such as the cadmium-selenium quantum dots, nanomaterials are made from toxic materials, or materials we know little about. For example, we know very little about carbon nanotubes' effects on human health. Therefore, we want to limit the use of carbon nanotubes for human consumption. So far, there are national and international agencies that are currently studying these risks and are developing updated rules and regulations on how to handle and dispose of nanomaterials.